Well, I've sort of overemphasized it even, maybe, this aspect of symmetry breaking. But before I leave you with whatever knowledge you acquired of the formalism, and in the last homework you presumably learned a fundamental thing, that when you talk of symmetry breaking, when a gauge group G breaks down through the vacuum excitation value that we say, which I sometimes call phi 0 or phi in the brackets, to illustrate that actually what happens is that we are talking of a value of the field in the ground state in the vacuum. This really should mean that I compute the quantum field, and that corresponds to the classical value. That breaks down to H, that the breaking is not unique. Well, obviously it's going to depend on the Higgs that you choose, that you've learned. It was different whether you took a doublet or a triplet. But it's more than that. Even if you fix your multiply, it depends on the parameter space of the model in question. With a doublet, it depended, for example, whether the mass square were positive or negative. So just trivially, if I take plus m squared, phi squared, I will get no symmetry breaking. The second derivative at 0 is positive. This is typically, okay, there could be multiple, there could be complicated situations with multiple vacua. But in a simple quartic potential, this assures that phi 0 is 0, and therefore H is G. There is no symmetry breaking whatsoever. If I take minus m squared phi squared, then surely I'm going to eliminate this trivial ground state, phi equal to 0. This is not anymore, it's not even a local minimum, right? Therefore, in this case, phi 0 is non-zero, and I know that H is not G. And presumably unique. Presumably there is no choice. But we could imagine some complicated big representation, a complicated group, leaving us with possibilities of different vector. In the simple example, as it took, the symmetry breaking was determined with one field. You took a triplet and you got SO2 when you broke SO3, right? You took a doublet and you broke it completely. Well, I'll illustrate just a little later how this may be changed. So the symmetry breaking depends crucially, obviously, on the choice of the group you start with. Second, on the choice of the representation that you like to work with. And third, even on the parameter space of the theory. Okay, I want you to keep that in mind. So last time we've ended up on the global case. Just a few more words. Still on the globally one case, on the choice of variables, doing physics is very often the art of choosing the right variables. And the Higgs and Goldstone are a beautiful example, especially Higgs, where choosing the right variable made all the difference. The historical development of our field depending deeply, profoundly, crucially, on choosing the right variables. Okay. Once that Hopf entered the game and chose the Romanizable gauge, okay, we can say the rest is history. Okay. The field that was stuck for a year blossomed. So in the global case, we said Lagrangian, remember, had no choice but having a very simple form. Then if I wanted to have fermions, I always sum over all the fermions. And in this case, there were two left and right Y spinors. Remember, I always start defining the fermions in their basic irreducible form, which is two components left and right. These are the irreducible representations of Lorentz group. Minus sign, interactions with right with plus sign, kinetic energy minus Yukawa. And you've seen this already. Ad nauseam, phi squared minus v squared over 2. Yukawa psi L phi psi r plus Commission conjugate. Notice that I put the bracket here when I write Commission conjugate. Strictly speaking, I should put it without a bracket because y can be complex. But why is it that I don't worry about y? The complexity of Yukawa couplings is one of the central issues of the standard model. It has to do with the CP violation. And it actually, the need to have a complex Yukawa coupling led to the extraordinary thing of predicting an extra generation of fermions, right? It's sorry, right, CKM, right? The KM. C was there before, okay, and it was real. And the point is trivial, that if you think that Yukawa is complex, we'll change the phase of psi r, which is 3, and it will become real. So if you have y equal y bar e to the I alpha, nothing prevents you from redefining psi r. So take psi r going to e to the minus I alpha psi r, and you will get rid of the phase. Trivial remark, but just to keep in mind, this is real. Okay? So I'm allowed to do that. So then we said, obviously, when I write 5, I want to emphasize a thing of crucial importance that I live near the ground state. And since I have 2 degrees of freedom, I should write like this. And the rest is known as a Goldstone theorem. In this case, okay, our examples, we took charge of phi to be equal to q left, to be 1, and we took the charge of qr to be 0. Notice this is, I'm not performing a symmetry operation here, I'm just redefining field. Okay? And fermion fields, the phases cannot matter, right? That's complex, and I can choose them any which way I want. So, well, the rest is a profound statement. mg, you can compute mg, and it is 0. You have to write the potential, and you will get from Yukawa, you will get this important interaction minus I and fermion over V, G, psi bar, gamma phi psi. So we have good shock now, see. Great. It should be obvious that you're not going to use some other variables, okay? Yet people from time to time like to do that. These are the most natural variables, right? And this, it will be sort of strange, okay? So this is a possibility A. I will just mention en passant because it's important. I can still write if I like. This, nothing prevents me, you agree? I was saying it's stupid, you're getting some very complicated interactions, so let me illustrate how complicated they are. The advantage of using this, notice that the potential forgets that G exists. So in the potential, well, I cannot make, I did this magic trick of making G disappear, okay? Weinberg or whoever. Higgs trick, the original thing going to the unitary gauge. I can't do that, okay? I don't have a gauge freedom, but still somehow potential doesn't know that G exists. So you can immediately write that mg is 0. You don't have to compute anything. See why this can be useful in a complicated situation if you generalize this. You will immediately read off a number of massless particles. But of course the guy exists. Why? Because the kinetic energy now is this guy. Or Yukawa, no, better. No, let's forget the kinetic energy. No, not kinetic. I made a mistake. I'll come to that. Yukawa will give me now, well, y psi L bar 1 over square root of 2 v plus h e to the I g over v psi r plus Hermitian conjugate. I can write like this. So what do I get? I will get y over square root of 2 v plus h. I can take out, you agree? It's real, and then I'll get psi bar psi cosine G over V. Do you see this? Or do I have to write it explicitly? I'll have E plus E to the minus. Just to write this, maybe it will be useful. This is psi r bar. Okay, V plus H. E to the minus I G over V. Psi L. So the first piece has 1 plus gamma phi, 1 minus gamma phi. So the one adds up into a cosine, and the other will give me plus I, psi bar gamma phi psi sine G over V. I'll let you for 1 minute convince yourself. This had 1 plus gamma 5, this 1 minus gamma 5, so you take a difference. When you take a difference, you get the sign. And there is a factor y, and there should be a factor of 2. No, because there is 1 plus gamma 5 over 2, so I think I'm right. I'm ahead of you still. You see, it was not so advantageous, okay? I have a complicated interaction. Notice that it immediately reduces. If I expand this will just be psi by psi. If I keep a linear term, this is the famous Higgs piece. And if I keep here a linear piece, I will get plus psi bar, gamma psi, G over V.
Why would you keep only the linear piece?
No, if I wanted just to see, because when I keep the linear piece, I go back to the, I have to check that I didn't make a mistake, because you guys were not telling me, yes, you're right. So, this particular use of variables, maybe I should strictly speaking call it phi prime to emphasize that reduces to the original one when I keep only the first term, and I have to recover in the linear form, and we are going to work with it. If you want to, study these interactions, use the linear form. It's much simpler. But you may sometimes want to know just what the particle spectrum is, and so it may be advantageous to do this. It may be. You should get used to it, or you will read a paper, you will read a book next time, and someone is going to write like this, and you should appreciate they are doing it just in order to read off the Goldstone bosons, but then, this interaction becomes more massive. So at the end, I should get the same result, whatever I compute, and I'm not going to now go into that. Or maybe I can show you one. Okay, what I can do, a little crazier thing to show you how you could get the same physics. There are people who say like this, okay? Well, I don't have a gauge freedom, but I can still do this. So your first reaction is what they're talking about, right? If your friend is doing it, okay? If it's not a professor, you're crazy. You can't do that. This is not a gauge symmetry. Well, I can just do that because then I have to make sure that I transform psi L. Psi L, they have the same charge. Okay? I'm making this transformation. This is not the symmetry of the theory. If it were, then she would disappear. But she can't disappear. And let me show you. As crazy it is, that may be useful for some reason. So psi L should also go as e to the minus G over V psi L. In this case, notice, of course, the potential, obviously, even here did not depend on G, right? So here, obviously, if I do this, then there is no mg, so mg is 0. It's even faster to read it here, you agree? If I do this crazy thing. There is no guy in the potential, okay? But look what I get. Allow me to erase now these things, and notice what I get from a kinetic energy. In the kinetic energy of psi, there was I psi L, gamma mu d mu psi L. Okay, this goes into I psi L e to the I g over v. I'm reading this crazy thing that I've done, gamma mu, d mu minus I g over v e to the minus I g over v psi L. You agree? I made this transformation. I did this. I'm changing variables, okay? I'm not claiming that this is a symmetry transformation of the theory. I want to show you that you can use the variables you like. And that there may be advantages in choosing one variable over another, okay? So this will cancel. Sorry, there is also a piece. Plus, of course, I psi L bar gamma mu d mu psi L. That piece remains. Okay, I'm just the change will give me this. Okay, and this gives me minus minus plus phi L gamma mu d mu g over v psi L. I'm going to integrate this by part. So this is d mu of everything minus g over v psi L bar gamma mu d mu psi L. Notice in this particular choice of variables what I achieved. What happened? Not what I achieved. Completely different interaction of Goldstone bosons, Nambu Goldstone boson. Now it has a oh, nobody objected. D mu. I don't know why I wrote what I wrote. Let's make it Lorentz covariant. It's d mu acting on everything. Of course, I'm just doing. There was d mu of g, and so it looks very different, right? Whereas in the original, the most natural variable choice, linear phi field, it has a interaction that I was stressing here. Has a hidden piece depending on the mass here, which is spin dependent and so on. We studied it last time on Monday. Here I got a derivative interaction. But let's continue just to see what we get. This is minus g over v, d mu. There is 1/2 psi bar, gamma mu, 1 plus gamma phi, psi. D mu, there are two pieces, vector and axial. What is the derivative of the vector piece? It's 0. This is a conserved current. Well, this is Dirac equation, if you wish. When I say that d mu phi bar gamma mu phi 0, this is equivalent to saying that I gamma mu d mu phi is m phi. This immediately will give you, okay, Dirac Lagrangian possesses that, okay, this is obvious, this, and you know what the symmetry is, it's a Fermion number, right? It's a phase redefinition of the no Dirac Lagrange, right? This is the central thing. I use it every time, okay? This has a symmetry. And this guarantees that the current is conserved. It's a Fermion number. Once you couple it to the electromagnetic field, it becomes charge, okay? At this point, it's just a number, and there is no sense of talking to charge if it's not coupled to anything. Okay? It just tells you that the free propagating Dirac field, you're not going to lose a particle, okay? That's going to be conserved. An electron stays an electron. But you can also derive it from the Dirac equation. That's how the things work out, okay? And therefore you act on left and right, you act on psi bar, and it gives you 0. And we did it a few times. If you act on the axial piece, you get the master coming out. There will be no cancellation because once you act immediately on psi bar, the other time you have to go through gamma phi. And we got here 2m So we'll get minus G 2m over 2v, and then there'll be a factor y. Psi bar gamma phi psi, or minus I, up to a sign.
Piece of minus I.
Let's be sure, in order to go, okay, from here, let me multiply it by minus I gamma mu d mu psi is minus I m psi. But in order for me to act on psi, I have to go through gamma phi. So it's going to become plus. That was right. Okay, it's going to be plus 2m. From here also I will have to derive I take a dagger. So what do I get? This is m psi dagger, and this is minus I d mu psi dagger gamma mu dagger. And what is this? This is minus I d mu psi bar gamma 0. Psi dagger is psi bar gamma 0. Agree? Gamma mu dagger. I multiply gamma 0 on the right, and I get m psi bar. So I get that minus I d mu psi bar. This is gamma mu simply. M psi bar. Which means that d mu psi bar gamma mu, where is gamma mu x? What am I? Okay, sure. So it's perfectly okay. So when I take d mu, I will have to multiply by I. You see, I'm going to get me m immediately because of the I. Here I go with a minus sign, and this becomes minus g over 2v times 2m times I psi bar gamma phi phi. Let me insist on this. Normally I don't on the sign. I don't insist on everything I write on the blackboard. But this I do. I'll never forget it. Okay, I was a beginning graduate student, and Ken Wilson came to give a seminar at City College, where I was doing my New York, when I was doing my PhD. And he was not yet Ken Wilson, but everybody was talking about this emerging genius. If you know, one of the great physicists that revolutionized our field. And he was giving a seminar, and there was T.D. Lee, the oldest, he came from Columbia, and he said at some point, I said, this sign is wrong. And Ken Wilson was looking at this, saying nothing. He apparently didn't talk too much. Looked back, stared at us, and we thought, oh, he's wrong, the sign was crucial. And he said, I don't guarantee for everything I write on the blackboard. I could be wrong. But this sign I do guarantee. And he wouldn't explain it, you know, and now you can't ask the guy to explain it. You told him he was wrong. Okay. I used this trick a few times when I was heavily attacked. You know, you give a talk and sometimes there will be people to attack you. You better be sure, okay, if they are glacial, for example. But it may be a good way of dealing with a stressful attack. So I don't want to guarantee for everything I write on the blackboard, but I think the sign is, anyway, up to a sign, we got the gamma phi spin-dependent interactions. You see, the choice of variables did not matter. It's just for me, in order to come here, I had to do some song and dance. some algebra. So what is useful in this particular way? Well, you have a sort of a form which does not depend on the model. You don't have to worry about writing Yukawa and whatnot. If you do this transformation, okay, you let the guy disappear from these interactions, it goes into a kinetic energy, you get a universal form for the number Goldstone boson. It always coupled to this. I don't care what theory talks about. I can prove it by making this choice of variables. I can go to a sort of, sometimes people even call this gauge. Of course, it cannot be called gauge symmetry. It's a choice of variables. People, we still use this sort of, we have cavalier language once we understand. When we meet, when we collaborators meet, then we simplify the language a lot. So a collaboration of 3,000 people becomes he or she. You can say, oh, he's stupid, although you're reading a paper of the whole, whatever. And you simplify the language, you speak of this gauge, okay? It tells you, and it tells you that it has to be derivative. When you gauge the thing, then this will become a phase, real phase, and therefore the interaction should be invariant under that redefinition. So it's not surprising that I got this derivative coupling. If you wish, the coupling in this picture is d mu g, let me write it, V psi L bar gamma mu psi L. There is a current associated with this, and it has always this form. And it's good to know that you don't have to go through the algebra of studying your complicated, big representation, many field situation of complicated interactions. Okay, I think I'll stop at this point. It can also help you to know that the results in one picture must agree with the results in the other picture. And therefore it may be sometimes for you useful to think of this before doing the calculation. Because in one picture you can see that, for example, an amplitude is 0. It has to come in the other picture, and there it will take some non-trivial cancellations to obtain that. And maybe I'll give you a homework to see that. Cannot overemphasize this, that the art of doing physics often the real phase is choosing the right variables, and you would maybe not to the same level that the fathers of the standard model chose them, but in having our little task to work on. The essential thing may be before plunging into a calculation to think of the variables you want to use. Okay. So now in this problem, before I leave the formalism, my hands are itching. I want to go to the standard model. I want to start finally teaching the modern standard model as the Higgs mechanism, spontaneous symmetry breaking, right, of the SU2+1 glacial model. You had a problem in the homework, the SO3 breaking with a triplet. Where phi was a triplet that you can write any which way you want. Some people write it as a vector, some people write it in this form, some people write it the way I'll start writing now. This breaks down into, what did you conclude? SO2. U1 or SO2 is the same. I don't care how you write it. SO2. Now, the triplets, which transform as usually every field transforms as e to the I theta t phi, the generator's characteristic of the triplets are the structure constants of the group. Okay. Now, it's in SU2 or SO3, it's obviously convenient to work with this. This you can never forget. They're just epsilon. But if I give you SU5, are you going to remember this structure constants you want? Even if I ask about SU3, if you studied, I'm sure you don't know the structure constant. I don't. So it may be more convenient that instead, so this was a vector, right? That instead of a vector, I go to the picture of the adjoint representation, which I can generalize to any group in a second. Okay. So what is an adjoint? When we had SU2, then we wrote the covariant derivative this particular representation to which the gauge fields belong, it's called adjoint representation of the group. Why? Because it has adjoint to the generators of the group. Okay. We never talk too much, but presumably with Sai, if you discuss it, you know how this transforms, right, under the SU2 group. You told me that you studied Yang-Mills, or even SUN. I don't care. I can generalize this to SUN. There will always be the same covariant derivative, you agree? The only thing that changes is the TAs. The TAs are the generators in the fundamental representations. Okay, TA are Pauli matrices in SU2, are lambda matrices in SU3, and so on. You know how to build these generators. If I ask you to build SU5, would you know how to build it? Doing at least SUN groups. It's just knowing SU2. All the generators, or all the SUN group are just made out of Pauli matrices, plus Cartan, of course. So maybe we could pause even for a second. If I want to build SU3, that's you've done. You've done SU3, right? We didn't. So how did the generators look like? Well,
Pauli matrices in the blocks.
I have to separate what I have to do. Before I start, however, I have to separate the Cartan from the rest. What is a Cartan subalgebra? What is Cartan?
Commute with every other generator.
Yes. Cartan is some of the generators, let's say T alpha, which mutually commute. Right? So what is the Cartan of SU2?
1.
1. And we call it sigma 3, we decided. Okay. So in SU2, this gives me T3. In SU3, it's called the rank. The rank R
Lambda 8 and lambda 3.
is a number in C, Cartan, right? In SU3, how many do I get? 2. And we usually take T3 and T8. In SU4,
3.
but think about this, okay? I have 2 times 2 traceless Hermitian matrices. Only one of them I can take to be diagonal. There are 2 in general, but the unity I can't take, okay? So when I said in SU2, it was trivial because it had to be traceless, so I took sigma 3 over 2, okay? And here, how many of these I can have? These are 3 times 3 matrices, which are diagonal. I can have 3, which are diagonal, but they are traceless, so there are 2. That kills 2. And so how do they go? Okay, T3, you say it's 1/2, 1 minus 1, 0.
So n minus 1.
And T8 would be then 1. It must be orthogonal. You always take the generators of orthogonal, so it must be 1, 1 minus 2. Okay, and then you have to normalize it, and therefore it will be 1/2, 1 over square root of 3, I guess. In order to get the same, we generalize, we normalize our generators of the fundamental representations in all SUN groups in a unique, uniform manner. Why do I have to generalize them? Why do I have to normalize this in SU2? Because every SUN group bigger than SU2 has an SU2 subgroup, and then they have to agree with its subgroup. So therefore, I have to normalize them the same way. And so I think there is square root of 3, check it. So in SU4, there will be 3 of them. The rank of SUN is n minus 1, but it's trivial. It's not some group theory. It's just a number of diagonal matrices which are traceless. Is n minus 1
Minus 1.
because they are traceless. Okay. So, and the rest, if I want to build SU3, what would I do? Well, the rest I put Pauli matrices. It's sort of a natural thing to start with. They are traceless. I have to, and they are Hermitian. I have to build up a basis of generators, which are traceless and Hermitian. And they are orthogonal to each other, so you would say, okay, put. So there will be lambda 1, you could quote, there will be a half. And then the rest is 0. And lambda 2? Well, put minus I here. And then I here. You put sigma 1 and sigma 2. And then lambda 3, well, I've chosen the name. Notice that why we call this lambda 3. This closes the SU2 subgroup that I identified. I decided to take the subgroup in the 1, 2 components. There was a convention. So lambda 3 is just completes it there, right? 1 minus 1, 0. This forms now an SU2 subgroup. And then lambda 4, how would you choose lambda 4? Well, just proceed. Put sigma 1 here now. There's nothing else to it. Lambda 5? It's embarrassingly simple to construct SU 127. Just put Pauli matrices in all possible places. The only thing that remains to the counting you will see is the Cartan. Let's see it in SU3 minus 1, minus I. So that's lambda 4, 5. I have lambda 8, I need 6, 7. Well, it's very easy, 6, 7. As I said, I'll put them now here. 1, 1. Minus I. And that's it. And it obviously works. I mean, if I take then SU4, Cartan now has 3 elements. Rank is 3, and these are usually taken T3, T8, and T15. How would the T3 look like in SU4? Well, the same. Just add more zeros. T8 would look the same, just add a 0. Okay, these two would look the same. Okay, 1 minus 1, 0, 0. I don't want to normalize them. 1, 1 minus 2, 0. T15? Orthogonal to both of them. 1, 1, 1. Minus 3. I finished. So I left with 12 of them. 12 is 6 times 2. There are 15 generators in SU4. 12 is 6 times 2. You will see that there are 6 possible combinations where you can put the Pauli matrix. Okay. If you know SU2, you didn't know that you knew. You actually knew all SUN groups. And already there is a problem number 2 in the homework which will utilize the SU3 somehow. Will make you know SU3 if you didn't know it. Okay, it may take time. You may struggle with the problem too. I expect you to struggle. If you don't struggle, then I'm suspicious. You are either talking to someone or it's a hard problem. I don't want you to get scared. I found it hard when I ran into it. Take some thought and some algebra. Well, look, algebra is enough. You can be done. I'm sorry if you wish. If you do the algebra right, you can actually get the result. Let me correct myself. As you know, if we compute, we don't have to understand all this. So you see, this way, we'll come back to this, of constructing. We could have an SU5 problem homework and exam. SU5 is nice because we'll talk about it when the last day of the course. So if I know the fundamental representation, I know it. For example, in SU2, I know it in my sleep. It's Pauli matrix. I don't have to worry about these things. But especially in SU3, which I don't know the structure constants, okay? It may be convenient then to define the adjoint representation. So there is an adjoint, often called sigma, which transforms the same way as the gauge bosons do. A mu A, TA, this representation transforms as U, A mu A, TA, U dagger, plus I over G, now maybe minus d mu U times U dagger, something like this. You've done this, right? Let's say, I would imagine you to have done that.
Without the TA?
If you do it without, oh, you did it without TAs. I mean, you wrote how a mu transforms. Then you will get F, A, B, C, theta B, A mu C. Is that how you did it? Then there is I over G, d mu theta A. There's a gauge piece always, okay? But I don't care so much about the local piece. I'm interested, you get the beauty of the Young-Mills is that the gauge field themselves form a representation of the group. They carry charges, if you wish. They interact with each other. Okay, they're very different from the photon, or if you wish, they transform. And this you must get derived. Okay? This is equivalent to this. I've already hinted at, well, I'll come to it in a second. I've hinted at. Why don't we come there? Okay, let me then arrive there. Okay, forget this previous knowledge. Let's pretend that you've never seen this before. It may help. So this is called an adjoint representation. Now this is a definition here. So that U is e to the I theta A TA, where TA are the fundamental generators of the group, okay? TAs are the Joe generators that you know. This Pauli matrix is mixed everywhere, plus the Katan, the things that you know. Okay, this is important. And sigma is written then as TA phi A. It's written as a matrix, obviously. I can always do that. What I'm doing, I'm taking, before I go on, before I write this, you agree that sigma dagger transforms the same way. Okay. I was hoping that you know this, but no harm if in doing it again. It transforms the same way. Therefore, irreducible representation obviously is the Hermitian one. Okay. I can now take sigma equals sigma dagger to simplify my line because they transform the same way. Okay. Notice how the trace sigma A transforms. Trace sigma transforms as is invariant. Trace U sigma U dagger is trace U dagger U sigma is trace sigma. So I can also take trace sigma 0, it will remain. You see, irreducible representation is making sure that you take the minimal piece of that possible field you're talking about, state representation of the group that has the same transformation properties. Okay? The trace will separately transform. But that means that I can write sigma as TA times phi A. I'm summing over 8, if you wish. I don't want to write that there is sigma summing over 8. Okay, sum over 8. Why? Because TAs are the basis of such Hermitian traceless matrices. So every Hermitian traceless matrix can be expanded in the basis of our generators of SUN. This is how they are formed. And this is why it always appears in this form. Okay. Now you've seen that the gauge fields are adjoint representation they define. Notice they have exactly the form that I defined by definition, okay? So I'm claiming, but let's arrive there. So how does sigma transform? Sigma transforms as, let's look at the small transformation to understand what is going on, right? I want to identify the generator. So this is 1 plus I TB theta B. I'm assuming some PA Phi 1 minus I TB theta B. It's a dummy index, so I can write it any which way. So I will get sigma. Well, why don't I write explicitly TA phi A plus I theta B TB TA phi A. Are you seeing how it's emerging, this transformation property that you've seen? Because now the structure constants enter the game. I'm generalizing the vector example of SO3. In the case of SO3, there will be 3 components here. I could still call the adjoint transformation, okay? This will be epsilon, but I want to do it for SUN. So this is TA phi A plus I theta B I epsilon B A C TC phi A. And this is TC phi C. I'm changing my dummy index minus theta B by epsilon F in general. I'm sorry. You can do that as well immediately. F BAC phi A. Right? Notice that this is phi C prime, is phi C, and let me put this minus F C B A theta B phi A. With shuffling of the signs, you will see precisely the transformation property of the analog. Okay, in the SO3, this is what we call adjoint representation efficient. Another reason to explain the name, that the elements, it tells you that the PA, so let's get it, maybe. I could write this as phi C plus I T, no, how do I want to write this? I TB theta B CA phi A. Let me put a head here to emphasize this is not the same generator I started with. The generators here, TA, are the generators of the fundamental representation. Please keep in mind. Okay. I want to read off the generators here. Something like this, am I right? This is how it will transform. There will be theta B with the appropriate generator, element CA, phi A, and therefore I conclude that theta B, TB, CA, I is minus I phi CBA. Theta B, CA is I multiply with minus I, I'll get plus I FCBA, which is minus I FBCA. This is how I define how I generalize this vector of SO3. Oh, go back to SO3 or SO2, go back to SO2, I will get precisely the epsilon symbol. So I've just generalized what we call a vector of SO3. Vector of SO3 is the adjoint of SO2. They must be equivalent. After all, it's impossible that they are not equivalent. This is 3 real components. This has 3 real components. Okay, they are not going to be 2 different vector representation. Okay, there is only 1 vector representation, so obviously a joint has to be equal to the other one, and we proved it here. Okay. Now, why would I go and work with this complicated object when I can work nicely with my vector? Because in SUN, it's a mess to generalize this. You have to remember the structure constants, okay? You see, we were in SU2. In SU2, this is a 3-dimensional representation. How do I generalize it, by the way, in SUN? How big is this representation? What is 3? I mean, 3 is many things. 3 is 2 plus 1, 4 minus 1, whatever. It's actually, this is equal to n squared minus 1. There'll be n squared minus 1 such components if and I read it off immediately. You see the advantage of using this particular choice. Making this particular choice. I think it's clear. These fields transform precisely what you've seen with SAFE as the structure constants. The generators are the structure constants of the group. But it's much more elegant, convenient, simpler way of bookkeeping. And I'll tell you why. You will see immediately how useful it can be. For example, there is some symmetry breaking, so there is a vacuum expectation value sigma 0. Now, these are constant. Sigma 0 goes into U, sigma 0 U dagger, and it's Hermitian. That means I can, without even doing any algebra, I can diagonalize it without any effort. I know that I can always go into the basis where this is diagonal. You know, it's all about choosing variables. When I study the symmetry breaking of SO3, I can work with the general, the phi 0 here is something that has phi 0 square equal to v square. So now I pick up a proper variable. I make a choice. I like to take this. You can make any other choice, okay? You and I should conclude, have the same conclusion to get the same physics, okay? So I can, and that of course you're telling me, well, if I have a vector, of course I can choose a vector to be in a certain direction, okay? So this is just choosing the z-axis. You agree? Well, in the case of a joint, I can diagonalize it. And that sort of tells me certain things immediately, because if I'm in a very complicated group, it will not be easy, it will not be trivial at all. You're not going to easily generalize it, you agree, to a complicated group, what happens. Now I've learned immediately, just by this simple thing, that the rank of, you know, so I have G breaking down to H through sigma 0, which is not 0, right? What do I conclude about the rank of H? it's equal to the rank of G. Why? Because sigma 0 commutes with all the Cartan, because they are diagonal. I mean, after all, what is this Cartan subalgebra? It's a set of diagonal matrices.
No.
So for example, in SO3, I know that the rank will be preserved, and that means something must remain, and that's SO2. Okay. I can read off immediately. Well, you can say, okay, you pretend you are smart. I can do that immediately, write like this, and I see that I can rotate inside the first two components. That's SO2. Okay, you can say we can do as fast. Okay, do it in do it your way in SU5. Take this funny representation. Okay, tell me how quickly you will learn the following. That suppose you and I have to study the breaking of SU5. Now you know that the choices are reduced. We can break into, say, SU4 cross U1. It has the same rank. The rank of SU5 is 4. This is 3 plus 1. Notice an interesting possible subgroup which has rank 4. It's SU3 and SU2 cross U1. Maybe it looks familiar? This also has rank 4. 2 plus 1 plus 1. Aha! You see how useful it is. Or you say, I have to break SU5. You are Georgi and Glesher, you are staying up in the night in 1974, you're discovering a beautiful theory of grand unification that can unify all the interactions. You know immediately what you're going to try. You want to take a simple Higgs, and you have to make sure that it keeps the rank. Oh, but the joint is very easy to work with, so you're going to try that. And lo and behold, it worked, and the rest is history. And you could sort of know immediately whether your representation is good or not. For example, if you take a fundamental, you know that the rank breaks. You did it. You took a fundamental of SU2 and you learned that SU2 got broken. For example, if I take SU5, and if I take a fundamental representation, I can take the value, you agree, in one of the components in SU5. Obviously, this is not the standard model, okay? We are wetting your minds to show you that you are now getting enough knowledge to be able tomorrow work on some aspects of beyond the standard model group theory, not physics. You agree immediately that I broke SU5 to SU4. That has a smaller rank. So I can't use this representation, which is natural, okay? You want to start with fundamental always, okay? But here you know that you would use the adjoint. And so the problem number 2 uses this sort of adjoint if you wish language way of writing, okay, that I strongly advise you to follow the way I did it in the homework and not to use the analogous working with structure constants. You can read those things much easier. If you do that, you will master this.
The rank of a group is the number of elements in the Cartan.
That's the number of elements in Cantor. That's a rank by definition. That's as you said, that's a number of mutually commuting generators. Okay. And we know what it means in this fancy language of group theory. It's just the number of diagonal matrices, which are traceless. So if I manage to get my VEF into a diagonal form, I'm okay. I can obviously do it because it was Hermitian. Every Hermitian matrix can be diagonal. This is simply choosing the freedom of the original theory. Because you will see, how do you write invariance? Okay, this is very important. How would you and I write invariance? Okay, I have to say a few words here.
I have a question.
Please.
Why do you have to preserve the rank? Or
Not always, but here I do.
if you want.
Here I do. I have to preserve the rank. Suppose I got an idea. I wish I had that idea. Of course, I was just a beginning graduate student, but I wouldn't have got this idea of Georgia and Glesher, okay, you know, 2 great physicists. One of them a master of group theory, or maybe both of them, but Georgia. There's a beautiful book of Georgia on group theory, by the way, very good for us physicists. There are a lot of nice simple tricks there that you can use. No, I don't know why. Do I have a good stroke? I guess I do. In this case, I have no choice. Because this had a rank 4. If I start with a group that has rank 4, and I have to get to the standard model that, well, in 74 they suspected, but today we know standard model is a good theory. For all that we know, it may be the last theory. Okay, I don't believe in that, but in principle you could say, who cares about going beyond, okay? It's good to a precision 1 in 1,000, okay? So we must pass through this step. At the energy is around 100 GeV to TeV, where we are doing our LHC experiments, okay, this is a good theory. Unfortunately, too good. You know, every day when I wake up in the morning and I click on, you know, on archive, hoping to see, you know, well, not so much, because by now I've learned that all the exciting news were always wrong. You know, there were so many anomalies in the last 30, 40 years in which people found deviations from the standard model, and they would last for a few months or a year, and they would all die off. You know,
The 750.
we are really 750 second Higgs-like looking, which wasn't Higgs, and so on and so forth. So now suppose that you like, now, which you ask me about the rank, you said, well, I don't like SU5. I don't want to work in SU5. I like SU6 for some reason. People study immediate deviation. Then you must break the rank. Then you say, it cannot be enough that I use an adjoint. I have to do more. Or suppose that you say, I don't like SU5, I like SU10. SU10 is the minimal grand unified theory that you will see unifies fermions also. It was invented by Georgia, originally, Fritsch and Minkowski. It's beautiful. This has a rank 5. I don't want to now teach you SU10, okay? In this case, to answer Stan's question, you better break the rank, okay? So you see, you can get a lot of useful information just by knowing you have to know the number of generators, obviously, where rank is fundamental, okay? Or what will be your potential choices. The typical thing you and I will do, within the task of breaking the group, try to take the simplest possible form. Imagine that there is a huge representation, much bigger than the adjoint, that keeps the rank. You would rather use a smaller one. You'd rather work with a doublet than a quintet or septet. That's kind of obvious. Unless, of course, you know a great deal of group theory and you want to write a paper and the guy already wrote a doublet, and then, people immediately found out that you don't have to use in SU5 adjoint. You can use something which is 75 dimensional and so on, okay? But you wouldn't do that as your first step, okay? Doing physics is going the minimal route. Obvious. So the invariance, well, obviously, you know what the invariance was sigma phi a square, which is phi transpose phi, the way I wrote it. So you see, they look the same, so what's happening? This is not the same choice. Or phi square, this is my choice. It's a great difference, huh? You see already the way it's written, but it feels. So how will I get there? Well, I take the trace, obviously, of sigma squared. Why? Because this is trace TA TV, phi A, phi B, and this is 1/2 sigma phi. Let me not write. Let's write like this, phi A, phi A. Not to write sigmas. The way I normalize. So this is the analog. There is 1/2, okay, when you want to normalize. Similarly, if I ask you how would you like how would you write the kinetic energy? Well, d mu sigma. d mu sigma. I'll take the trace, obviously. And that will give me again trace A TV. d mu phi A. d mu phi B. And so that's 1/2. For example, now it's normalized immediately. And so on and so forth. If I have a gauge symmetry, obviously this will just become a covariant derivative. See the idea of covariant derivative, why it's called a covariant, it transforms the same way as ordinary derivative. So if the fields transform as u psi, d mu of psi, it transforms as u d mu of psi. This is the covariant derivative. It keeps the transformation property, and this is why it has to be modified in the case of local gauge transformations, right? Because ordinary derivative then wouldn't transform correctly, and so on and so forth. And it's sort of nice to use this language, because then you are kind of bridging the gap between what is formal transformation properties in the scalar sector and the transformation properties of gauge fields. Notice they always come as adjoint. So it's good that you know this language. Any gauge group in the world, the covariant derivative tells you that these guys transform. So make use of that. It's much more convenient than working with components, okay, to work with this matrix. Once again, traces and permission. Okay. So this is what I consider group theory. For me, group theory is knowing SU2 well, and if you know the fundamental and adjoint, okay, then very often I see you guys come here knowing fancy sort of group theory and not being able to deal with the... Make sure that this becomes familiar to you. This will be so beneficial, okay, much more than the formalism behind it, okay, yeah. Any questions here? So we've seen that adjoint, make sure the rank of A is a rank of G. Whereas fundamental, make sure that rank of A in SUN is rank of G minus 1. We'll break the rank. Just by rotating, I will see what remains is just the SUN reduces to SUN minus 1. I don't have to do the calculation, right?
H is a new group that is...
This is what I've been using. Let me write once again. What we are studying throughout, well, we won't continue so much, okay? What we study in the Higgs mechanism is going from G to H through the vacuum expectation value of some, okay, generically, some field, which is non-zero. H is the resulting group. G is the starting group in the conventional notation, and most people use this notation. Estelle.
What happened with the vacuum manifold in both cases?
Very good question. Very good question. Well, in the case of, I want to do it case by case, the vacuum manifolds get more complicated. It's not a simple field theory, but in the case where G was SO3, and phi was sigma, was adjoint or vector. What was the vacuum manifold? It's phi1 squared plus phi2 squared plus phi3 squared equal v squared, and this is called S2. It's a two-dimensional sphere. If I take the same group, well, I have to call it SU2, and then phi is a doublet. It's complex, so I cannot call it SO3. Then what is the vacuum manifold? Now there are 4 real components, okay? That was the trick, okay? I remember Guillermo said it the other day. Well, I have to remember to write the doublet like this now. So this gives me phi1 squared to phi4 squared
Yes.
equal to V squared. And this is S3. And so on and so forth. And I have to look at a particular case to answer that question. Okay, I can't answer it generically. What the vacuum manifold is. That depends on the grouping question. Obviously, that gets rather complicated by enlarging our gauge group. Well, that of course makes it interesting also. It may be harder to do, but then there is something to study. The topology of symmetry breaking becomes something that you can write a paper on when the group is not trivial. People do. So the dilemma that the fathers, Weinberg and Salam had, and which is made clear in the Weinberg's beautiful 1967 paper, it was a dilemma which Higgs to use. I want to be minimal, right? What we face in the standard model, what was faced by the father is which Higgs I use to break this symmetry. I don't have to write color because color is not broken apparently, okay? We'll come to that. Why we believe that? This we know is broken and we know that the symmetry of the world, we don't have to think about that, that's established for us. It's only U1 electromagnetism, you agree? There's no other symmetry. The other gauge fields are very heavy. So that means this is equivalent to having SU2 broken to nothing. This will be G, this will be H. Which representation should I take? It's a doublet. You've tried. Well, I could have asked you to try the quartet and quintet and so on. Okay, I stopped with a doublet and triplet. And then you say, I better take a doublet because with a triplet I would have here U1 and then there is an extra U1. SU2 breaks to U1, I wouldn't complete the job. I may add another field. But if you want to be minimal, we want to try to do it with a single field. So I'm going to try to use a doublet. Actually, there is more to it. I could actually see that I needed a doublet. If I take this as a fundamental principle, that is, I cannot break symmetries explicitly. I can't. I will have a non-normalizable theory. I will have bad propagation. Therefore, I must use the Higgs mechanism. It's not easy to promote such a principle before you even know that that's true. I give you a hint why this may be true. You know, I've tried to give you with this rudimentary field theory knowledge that we have to show that it has to. Therefore, even fermions should get a mass from the Higgs. But remember in the standard model, the fermions go like this. Let's take quarks. So let's imagine that I want to write a mass term for the down quark. It has to be of this form, UdL dr. Agree? I must work with the underlying representations in order to preserve the original symmetry. I'm not allowed to break it, okay? It may happen at the end. The vacuum does it for me. But this, of course, it's not invariant. So I can't write the mass term for the down quark. And the problem is that this is a singlet, and this is a doublet, or if you wish, doublet dagger, to be even more precise, which is sort of equivalent. So therefore, the only thing I could do here is to write another.
Metric.
Another?
Vector.
Doublet.
Doublet.
Doublet. The only thing I can write here is a doublet, because the only invariant you can form with a doublet, the only field that can help your doublet to be invariant is a doublet. So I can put here something. It must be a scalar. Lorentz symmetry tells me. Okay, this is already scalar. So I'm forced, if I want to have something resembling the resulting physics of fermion masses, my only hope is a Yukawa interaction. See, I arrived there. I can do it by writing a Yukawa interaction. I will call now Yukawa Dirac this. But ideally I should put a doublet here. So in any way I have to put a doublet. And then you learn that the homework doublet actually does the job of breaking SU2, okay? So, yeah. We have thought of on the right track. You can imagine the excitement that it seems now maybe that I can get everything done with just one field. Okay? Let's try to construct a theory beyond the standard model and you will see that the Higgs sector becomes a mess. Let's think a little more now that I studied it. I should do that for the up core too. Now if I do this for the, what to do now? I can try to put phi, but this won't work. Let's see why not. Let's now find out what the hypercharge of phi is. Remember that the magic formula is Q is T3 plus Y over 2. So let's write it better. Y is 2Q minus T3. This is actually the way it works. I know Q. So for example, dr, what is, so let me write hypercharge here. Unfortunately, hypercharge, okay, and Yukawa. Should be clear from the context. Confuse you. So what is the hypercharge of this? It's minus 2/3. T3 0. And this guy, y plus y, I sum it twice. This is 2 Q up plus Q down. So y is Q up plus Q down in a doublet. So the hypercharge of a doublet is the sum of charges because T3 sums to 0. So 2/3 minus 1/3 is 1/3, but this is bar, so minus 1/3. So what's the hypercharge of phi? Plus 1. Okay, Lagrangian must be invariant. You cannot carry hypercharge. You cannot carry any charge in the world. So I want to do this very slowly, very carefully. Okay, I can't have you miss the essence of the standard model. But what should I do here? This is now different. This is 4/3, and this is minus 1/3. So this is minus 1, but this has plus 1. Phi? Well, there's no bar. This is not the fermion field. Phi dagger.
Phi dagger, yes.
Well, I can't put phi dagger. This is anti-doublet. Look, phi transforms
Yes.
as u phi. I'll call this Q, QL, transforms as u QL. So QL bar transforms as QL bar u dagger. This is why this was invariant. I didn't even write it because it is obvious, but this is how it worked. This is a singlet. Okay, for example, this worked into the same thing, u dagger, then u, and here 1 for the singlet, no? And this was 1. So I can't put phi dagger, it wouldn't work. I can't make it lie down, you know, this is lie down. I have to have a spinner standing up. But it has to have the opposite hypercharge. Well, if it's not dagger, it's phi star. But even this is not invariant. Because phi star transforms as u star. Phi star.
You start transpose.
Yes.
But
Transpose.
well, if I transpose it, I'm making it lie down.
No, lie down again, yes.
No, you see, You see what I did now? This is an anti-doublet. This is an anti-doublet. Okay, a little lesson on the dilemma I have is similar to the following, and we had it in quantum mechanics before. If I have two doublets, I don't want to. Okay, let me use D for doublet. Generically, it can be fermion UD. So how do I form invariant? One invariant is D bar D, D dagger D. Let's imagine two different even, I don't care. Okay, yeah. So I have a set of doublets. One way of making it invariant is take this. Why? Because this transforms as D1 dagger, U dagger, U D2. Notice the beauty of non-abelian physics, non-abelian group theory, non-abelian mathematics, non-abelian Yang-Mills thing, that all the representations with the same quantum number transform the same way. Okay, that's different from U1. There, unfortunately, we have no quantization, no commutation rules. And charges are arbitrary. So this is invariant, you agree? So obviously, if I take a spin half, an anti-spin half, you know, I take something pointing here and pointing here, I'm gonna get 0. There is yet another invariant that you're actually even more familiar with what we did when I want to get spin 0. After all the representations when they are built of the fundamental that you do by symmetrizing and anti-symmetrizing, that's group theory. So this is also an invariant. D1 transpose epsilon D2. Where epsilon is the anti-symmetric matrix. This can be written as D1 transpose I sigma 2. That's after all D2. So that transforms as D1 transpose U transpose I sigma 2 U D2. Now U transpose is EI theta T transpose. So what is the difference between the sigma 2 and the rest of the Pauli matrices? That sigma 2 is anti-symmetric. But sigma 2 commutes with sigma 2. If I want to be specific, this is e to the I theta 1 sigma 1 over 2 minus theta 2 sigma 2 over 2 plus theta 3 sigma 3 over 2. Right? There is a very important difference that I get a minus sign here. But then, however, it commutes with sigma 2. These guys are plus here, but they anti-commute with sigma 2. So this is very easy to see immediately that this is D1 transpose. I sigma 2, no, D1 transpose, yes, I sigma 2, I'm going to move it to the left. So when I move it here, this will keep the sign. The guy will change the sign because the anti-commute is sigma 2. So you will get E, let me be specific, E to the minus I theta A sigma A over 2. But U, which is there, is E to the I theta A sigma A over 2. If you wish, this was U dagger. U. D2. So this is D1 transpose, I sigma 2, D2. You've known this for years. Anti-symmetrizing spin gives you an invariant. I don't have to take the anti-spin. And you have precisely this situation here. Just the Hermitian conjugate of what I've done. See, this has now +1. So this is okay. Let me just show you what you have here. So this transforms into UD bar L, U dagger. I'm going to put I sigma 2, I sigma 2, U star. Why will I do the same? Because I have precisely this situation. I have, you see, I have two real D1 and D2. Here I have two complex. I have a star and I have a star hitting here. And it's very easy to see that this is by the same procedure as before. This is U I sigma 2. Why? Because U star, which is e to the minus I theta A sigma A star over 2, mistreats here sigma 2. But sigma 2 commutes with sigma 2. U star is this, you agree? Well, it should be. Everybody follows? Mm-hmm. So I have I sigma 2 U star. Sigma 2 commutes with sigma 2. So here this is e to the minus I theta 1 sigma 1 over 2 plus, pardon, minus theta 2 sigma 2 over 2 plus theta 3 sigma 3 over 2. So I sigma 2, when it goes through, what happens? It commutes with sigma 2, and then that commutes here. So it changes the sign here and here, and keeps the sign. So I get e to the I theta A sigma A over 2, I sigma 2, which is U I sigma 2. Okay. Okay, the thing to remember is what I've written there. U transpose I sigma 2 is I sigma 2 U dagger. This is equivalent to I sigma 2 U star is U I sigma 2. This is simply what I'm saying, that when I symmetrize two spins, I will get spin 1. But more important in this case, when I anti-symmetrize, I'll get spin 0. So in this case, I symmetrize spin, and here I anti-symmetrize, and here I have anti, so it's the same thing, right? Okay, so spin half, which is to say that in SU2, as you know, there are no really complex representation, they're pseudo-complex. Spin half and spin minus half are equivalent to each other. You don't get a new representation. You cannot do this in any SUN group. You will not take the 3 of SU3. If I anti-symmetrize 3 of, let me repeat this. So in other words, okay, this is a miracle of SU. All I'm saying here is the 2 times 2 product of two doublets is symmetric plus anti-symmetric, which is 3 plus 1. If I do it in SU3, very easy to count. Symmetric is 6. So anti-symmetric is actually 3 star. It turns out you have to distinguish in SU3, 3 and 3 star. We'll find these situations. Okay, I'll talk to you about it. Okay, well, how do you know that? If you multiply once again by 3, if you anti-symmetrize 3 times, you should get a singlet. In SUN group, you have to keep anti-symmetrizing to get a singlet. Okay. And that you know, because if I multiply this by 3, I will have a lot of things, but 3 times 3 star gives me a singlet. Okay, that's trivial. It's very easy to get a singlet by taking a representation and anti. That's going to immediately give a singlet. I can also get a singlet if I keep anti-symmetrizing. In SU2 once, in SU3, I have to take 3. Why is it that I have to do that? Just to think about that. Phi I in SU3 transforms as Uij phi j. So if I take epsilon ijk phi I phi j phi k, that will transform is epsilon ijk ui I prime ujj prime ukk prime, you agree? Time, let me write here, phi I prime, phi j prime, phi k prime. But what is this? This is epsilon I prime, j prime, k prime, determinant u. This is how you get determinant u. But you have to think a little bit about it. You should know that. Okay, I'm not teaching group theory. Okay, I wanted you to remember these few things. You know how to get singlets. Okay, and how to build an adjoint. Okay, if you know how to do that, if you know how to build an adjoint, well, hopefully other representations. Okay, then you start to know group theory. And Julian is tired, right? We shouldn't keep on. Right? You see well, of course I'm there, but there is a body. Body language. We have I love tennis. I've been watching a lot of tennis. They were great tournaments. You can see how the match is going by looking at the body language of a player. At the beginning, it's all there. Well, it's funny when you teach. It's sort of opposite. You notice when you have to give a talk, you don't want to stop. I don't know if that happens to you. It gives you energy. We have this double. I have a personality split. And when I listen, I want to sleep. Normally. So I understand you well. Okay, so we could wrap it up. We decided that we are going to pursue the singlet. But make sure, this you were supposed to know. Okay, this is the basics of the group theory. Okay, that's SU2. Okay, I find out that this is sort of a weak generation after generation. Somehow, that's why I go through that. It's a weak spot. Somehow, group theory can still be taught formally. So what we have to do, if we have muscle on Friday, build up the standard model. On Friday we can do that. You see, it's all going to come out. Okay, there'll be a lot of details to follow, but if I use the blackboard nicely in the time on Friday, I should be able to show you how the essence of the standard model emerges. That requires that you feel comfortable about the Higgs mechanism, that you think you mastered it, at least in the SU2 case. SU3 is going to be tougher, but we don't have to worry on Friday about that. And this group theory, okay? Please think about what I said today. Check it, go. It's just a few minutes. And ask me a question, write to me or ask me or whatever. I don't want you to fall behind on this.
think it's the other one.
I think it's the square.
It's good.
Yeah, of course. He went on with all the drama, you know.